Hey you guys, this is Mr. Millings, and in this video we are going to do some weak acid and weak base calculations. And before we start doing some calculations, here's a little disclaimer for you. It says that prior knowledge of the topic below is essential before watching this video, and I recommend that you first watch the video on calculating ion concentration using the pH scale. So what is a weak acid? What is a weak base? And how can we do some weak acid and weak base calculations? Well, let's jump right in and take a look. And so what is a weak acid? It says right here that a weak acid is an acid that partially dissociates in water. And the comparison between the concentration of dissociated ions a weak acid produces in water to the concentration of the weak acid that did not completely dissociate in water once equilibrium has been reached is known as the acid dissociation constant, or Ka. So what does this mean? Well, let's take a look down here at what's happening. We have down here acetic acid. And we know that acetic acid is a weak acid. From an earlier video, we learned about the 6 or 7 strong acids and how everything else is going to be a weak acid. So we have a weak acid right here, and when we put this in water, it's going to partially dissociate. It's not going to dissociate completely, and according to the Brønsted-Lowry model of acids and bases, this hydrogen right here is going to get donated to this water molecule right here, producing hydronium right here. And when this H plus gets donated to this water right here, it's going to leave behind, or it's going to produce acetate ions over here. All right, so according to the Brønsted-Lowry model, acids are H plus donors and bases are H plus acceptors. So what ends up happening in this chemical reaction, because we have a weak acid here, is the forward reaction does not take place as much as the reverse reaction. What ends up happening with weak acids is that this phenomenon right here takes place at a very, very, very low rate compared to the reverse reaction that happens at a much higher rate. So if we take a look at the amount of or concentration of dissociated ions in a weak acid, there's not going to be very many compared to a strong acid because the reverse reaction is taking place at a much higher rate. These two substances here are reacting together to produce acetic acid and water. And keep in mind that when we're talking about acid strength, it's all about the hydronium ions that are in solution that relate to the pH value of that acid, or how strong or weak that acid is. So there's not going to be very much of this in solution because the reverse reaction is taking place at a higher rate. This is reacting with this to produce these two things. And so the comparison between the amount of dissociated ions in solution to the amount of the weak acid that did not dissociate here is called our acid dissociation constant, or Ka. And we can refer to a table in a book or on the internet and find the Ka value, or the acid dissociation constant, or the equilibrium constant for various weak acids. And if we take a look at acetic acid, the Ka value is 1.76 times 10 to the negative fifth. And so it says right here, the low Ka value tells us that the acetic acid does not dissociate much in water. This is a very small number, so it doesn't dissociate much in water. And as Ka approaches 1, the acid becomes more acidic or stronger. And if Ka is greater than 1, then the substance is going to be a strong acid. And so how do we calculate the Ka of a weak acid? Well, to calculate the Ka value of a weak acid, in other words, how do we end up with this right here? It's simple. We take the concentration of the two ions that are produced in water. So we take the concentration of acetate ions in water times the concentration of hydronium ions in water, and we're going to divide it by the concentration of our weak acid, in this case acetic acid right here. And we can essentially ignore water when we're writing our equilibrium constant, or Ka value, or Ka expression, when we're writing our equilibrium expression. All right, so a weak acid, once again, is an acid that will not completely dissociate in water because the reverse reaction here is favored. It's happening at a much higher rate than the forward reaction. So let's take a look now at weak bases and talk about what a weak base is. And so what is a weak base? Well, very much like a weak acid. A weak base is a base that partially dissociates in water, and the comparison between the concentration of dissociated ions a weak base produces in water and the concentration of the weak base that did not dissociate in water completely, once equilibrium has been reached, is known as the base dissociation constant, or Kb. So what does all of this mean? Well, let's take a look at an example down here. We know that ammonia is a weak base because it is not one of the strong bases that you were asked to memorize. So we have a weak base right here, ammonia reacting with water. And what ends up happening when we take ammonia and we put it in water is this. Water is going to donate an H plus to ammonia. And so according to the Brunstad-Lowry model of acids and bases, because our water is donating an H+, our water here is our acid, and because ammonia here is accepting our H+, it's going to be a base. And so what ends up happening is when water donates an H+, it's going to produce hydroxide ions that are floating around in our solution over here. And when this base accepts an H+ from our water, it's going to end up producing our ammonium ions floating around in this solution. But what is also happening is this. These ammonium ions are donating an H+ to our hydroxide ions to produce our water over here. And when the ammonium ion loses an H+, it's going to end up producing our ammonia over here. And so whenever we have a weak base, the reverse reaction takes place at a much higher rate than the forward reaction does. Okay, so we're not going to have very many dissociated ions because these two dissociated ions are reacting with one another to produce our weak base over here. And that's what ends up happening with a weak base. And ammonia is a weak base. It does not dissociate completely in water because the reverse reaction takes place at a much higher rate than the forward reaction does. These two dissociated ions are reacting with one another to produce our weak base over here. And so what we can write is an equilibrium expression, or Kb value for this reaction right here, or for our base. And we can actually look this up in a reference book or in a textbook, but basically what this value tells us, 1.8 times 10 to the negative fifth, this is comparing the amount of dissociated ions to the amount of our weak base. Concentration amounts, that is. And so it says right here the low Kb value, we have 10 to the negative fifth. This is a very small number. This tells us that the ammonia does not dissociate much in water, and as Kb approaches 1, the base becomes more alkaline or stronger. And if Kb is greater than 1, then the substance is a strong base. So understand this concept, that the Kb value here is a relationship between the dissociated ions and the weak base. And because this is a very small number, that is telling us that we hardly have any dissociated ions in solution at all. And so how can we write our equilibrium expression for our weak base? Well, what we can do is we can take Kb equaling the concentration of ammonium ions times the concentration of our hydroxide ions divided by the concentration of our weak base ammonia right here. So understand that concept of weak acids versus weak bases. Let's take a look now at a table of weak acids and weak bases, Ka and Kb values, and then go ahead and apply that to several different problems. And so what we're looking at here is a table of Ka and Kb values of weak acids and bases. And the Ka and Kb values of weak acids and weak bases is generally reference material that can be found on a table in most chemistry textbooks or on the internet. Alright, so if you take a look on the internet and Google this, this is what you might see. And so if we're taking a look here at our acids on the left-hand side, we know that sulfuric acid is a strong acid. And so our Ka is going to be greater than 1. But if we're taking a look at some other Ka values, here you go. You see phosphoric acid is 6.9 times 10 to the negative third. Very small number. Hydrocyanic acid, 6.17 times 10 to the negative 10th. So, very, very, very small amount of these ions are going to dissociate in water. Same with hypoiodous acid. If we take a look, 2 times 10 to the negative 11. If we take a look on the right-hand side, we have our Kb values. Ammonia is a weak base, and here is its Kb value we just talked about. We have hydrazine right here. N2H4 is going to be a weak base with a Kb value of 1.7 times 10 to the negative 6. So what we can start to do now is using these Ka and Kb values, we can start to calculate and determine the pH values of weak acids and weak bases. So let's go ahead and start to use this table right here to figure out the pH of weak acids and weak bases. In this problem, it says to calculate the pH of 0.20 molar acetic acid, and our equilibrium constant for our weak acid is going to be 1.8 times 10 to the negative 5th. So before we start figuring out the pH of this acetic acid right here, we first must show and write the chemical reaction that's taking place. So we have acetic acid, which is HC2H3O2, and this is going to react with water. It's in solution with water. And so we know that this is going to donate an H+ to our water, and this is going to produce C2H3O2- ions in solution, as well as H3O+ ions in solution. And we also know that because this is a weak acid, these two things are reacting with one another to produce these two things over here. So we have an equilibrium that has taken place here. An equilibrium reaction that's taken place. And so there we go. And so what we now need to do is we now need to figure out the pH of this weak acid that we have right here of 0.20 molar acetic acid. So in order to do this, let's figure out what our equilibrium expression is going to be. To get our equilibrium expression, or Ka, we're going to have to take the concentration of our two reactants, or our two ions over here, the concentration of C2H3O2- times the concentration of H3O+, and we're going to have to divide this by the concentration of our weak acid, HC2H3O2. And when we're writing our equilibrium expression for our weak acid, we can ignore water. We don't need to include water in our equilibrium expression. So here's our equilibrium expression right here. So what we now need to do is we now need to figure out the concentrations of each one of these ions, and the way that we can do that is by setting up an ICE chart. ICE stands for initial concentration, change in concentration, and equilibrium concentration. And so if we take a look, we have our reactant, which is our weak acid, HC2H3O2, and our two products, which are our two dissociated ions, C2H3O2- and H3O+. And so initially, our concentration of our weak acid, it tells us, is 0.20. So the initial concentration of these two things initially is going to be 0. We're starting off with none of this. And so what's going to end up happening is that this is going to react with water, and so there's going to be a change in concentration, and we can label this as negative X. And we can label it over here as positive X. And so what is the equilibrium concentration going to be? Well, we can just add these two together. We'll take 0.20 minus X. This will just be X, and this will just be X. And so there we go. We now know our values for our equilibrium expression that we can place right into here. So let's go ahead and do that. And so if we take a look right here, what this is telling us is that Ka equals all of this. Well, we know our Ka value, it's right here. So we're going to go ahead and substitute our Ka value, which is 1.8 times 10 to the negative 5th. And this is going to equal the concentration of our acetate ions, which we see right here is X. times the concentration of our H3O plus ions, which we also see here is X. And we're going to divide this by the concentration of our weak acid at equilibrium, which is 0.20 minus X. And so we can assume right here that X is going to be a super small number. Because this is a weak acid, it's not going to dissociate much. And so X is going to be a very small number. In fact, it's going to be negligible right here when we subtract it from our initial concentration of the weak acid. So we can take a giant leap here. And what we can do is we can just ignore the X right here in our weak acid equilibrium concentration. And so what we'll end up with here is this. We'll end up with 1.8 times 10 to the negative fifth equaling X squared all over 0.20. And so how do we get rid of this fraction? Well, we're going to cross multiply. And if we cross multiply, we're going to end up with X squared equaling 3.6 times 10 to the negative sixth. So how do we solve for X now? We're going to take the square root of this, and we're going to end up with 1.9 times 10 to the negative third. So X is going to equal 1.9 times 10 to the negative third. This is not our final answer. This is just the concentration of our H3O plus ions. So this is going to equal the concentration of our H3O plus ions that have dissociated into the water. However, the question is asking for the pH. So in our final step, what we now need to do is we now need to figure out the pH of the solution. And remember, to get the pH of a solution, we take the negative log of our H3O plus concentration. And that's what we just figured out. We figured it out to be 1.9 times 10 to the negative third. So we're going to take the negative log of 1.9 times 10 to the negative third. And if we do this, we're going to end up with 2.72. Or 2.7 if you are using the correct number of sig figs. So what is the pH of 0.20 molar acetic acid? It's going to be 2.7, and that's how we calculate the pH of a weak acid. Let's take a look at another example where we can calculate the pH of a weak base. In this second example, it says to calculate the pH of 0.75 molar solution of ammonia, or NH3. And if we look on a table of Kb values, we can see that the Kb value for our NH3 here is 1.8 times 10 to the negative fifth. So the very first thing that we have to do is we first have to write the chemical reaction for what happens to NH3 when we put it in water. We know that NH3 here is a weak base because it is not one of the strong bases that we spoke about in an earlier video. So let's see what's going to end up happening. So we have NH3, and when we put this in water, what ends up happening is that the water here is going to donate an H plus to our weak base right here. It's going to accept an H plus. And so according to the Brunstad-Lowry model, this substance right here would in fact be a base because it's accepting an H plus from our water here. The water is donating an H plus, so it is an acid in this case here. And so when this happens, when this donates an H plus to our NH3, we're going to end up with NH4 plus over here. And when this loses an H plus, it's going to produce OH minus ions. But because we know this is a weak base, what is also happening is that the reaction going to the left is also taking place at a much higher rate than the forward reaction. So the reverse reaction is favored here whenever we have a weak base. And so what's happening here is that NH4 is donating an H plus to OH minus to produce our water here. And when this loses an H plus, it produces ammonia right here. And so what we can now do is we can now write our Kb expression for this chemical reaction right here. And so Kb is going to equal the concentration of NH4 plus times the concentration of OH minus, all divided by the concentration of NH3. And we can always leave out water out of our Kb expression here. So here is our Kb expression for the chemical reaction that we see right here. And so what we now need to do is we now need to set up a little ICE table, What is an ICE table? I stands for the initial concentration, C stands for the change in concentration, and E stands for the equilibrium concentration of these three substances that we see right here. So if we take a look, the initial concentration of NH3 is 0.75 molar. We won't worry about water. We're going to leave this out of our Kb expression here. And so what's going to end up happening is we are starting initially with no NH4 plus, and we're starting initially with no OH minus ions. And so if we want to know the change, what's going to end up happening is that the chemical reaction is going to take place, and there's going to be a change in the concentration. The concentration of NH3 is going to decrease by, we will call X, minus X. And the concentration of NH4 is going to increase by a positive X here and a positive X here. And we'll notice that the stoichiometric relationships between these three substances is 1 to 1 to 1. That's why we have negative X, and positive X. And so here is the change in our concentrations. So what we now need to do is figure out the equilibrium concentrations, and the way that we get that is by taking 0.75 minus X here, and this will end up being X, and this will be X right here. And so now what these numbers here represent, or what these values represent, are what we see right here in our Kb expression. So what we can now do is plug this into our Kb expression. So let's go ahead and do that next. So Kb, which we see right here, is 1.8 times 10 to the negative fifth, is going to be equal to the concentration of NH4 plus at equilibrium, which we're calling X, times the concentration of OH minus at equilibrium, which we're also calling X. And we're going to divide this by the concentration of NH3 at equilibrium, which is 0.75 minus X. And so let's think about this. Because we end up having a weak base here, the forward reaction is not favored and the reverse reaction is favored. So the amount that NH3, the amount of concentration that NH3 is going to lose right here is going to be super small. That's what makes this a weak base right here. In fact, it's going to be so small, this is almost negligible. If we have 2 sig figs here, this number is going to be so small that when we subtract this minus this, we're still going to end up with 0.75 if we use the rules of sig figs. So because of that, what we can actually do is just cross this out here. And so we end up having 1.8 times 10 to the negative fifth equaling X times X all over 0.75. And if we carry this a step further, we'll end up with 1.8 times 10 to the negative fifth equaling X squared all over 0.75. And so if we cross multiply now, we're going to end up with X squared equaling 1.8 times 10 to the negative fifth times 0.75. And when we put this in our calculator, we're going to end up with X squared equaling 1.35 times 10 to the negative fifth. Let's solve for X. We'll take the square root of both sides here. And so X is going to equal 3.67 times 10 to the negative third. And so, if we take a look, that is going to be our concentration of OH minus, right? So the concentration of OH minus equals 3.67 times 10 to the negative third moles per liter. And so now let's go back to this question. We want to calculate the pH of this solution. Well, we know the OH minus concentration here. And so how can we calculate the pOH? Well, to get our pOH, we are going to take the negative log of our OH minus concentration, which is the negative log of 3.67 times 10 to the negative third. And when we put this in our calculator, we're going to end up with a pOH equaling 2.44. However, this is not our final answer. The question is asking for the pH of this solution here, or of this ammonia. So what we have to do now is figure out the pH. To get our pH, we're going to take 14 minus our pOH, 14 minus 2.44, and we're going to end up with a pH of 11.56. And this is going to be our final answer right here. So what is the pH of 0.75 molar solution of ammonia? The pH is 11.56. If you like what you see, go ahead and click that little bomb in the bottom right hand corner. That's going to subscribe you to my channel. And feel free to leave any comments or questions in the comment section down below. And I really hope you guys found this helpful.